Hello. In this video, we're going to cover Lab 8, which introduces the foundational tools for doing inference. So this lab signifies a turn in the course where we're now not just doing statistics on individual situations or distributions, but we're wanting to make inference on those statistics. So what does this mean? I'm going to draw this picture again because I want to get it into your brain. Inference involves when we have some kind of population, it's unknown, and we take a sample, and based off our sample, we have some kind of statistic. And we're going to use that statistic to make inference about the population. And depending on our sample size n, as well as other factors, we'll be able to determine some kind of certainty with which our statistic, maybe p hat, sample proportion, represents something in the population. So that is inference in a nutshell. And it's a difficult thing. It's a difficult concept because we're trying to describe something we do not know and with some kind of certainty based off a fair amount of theory. So I hope I explain this clearly as we go forward. Hope these examples illustrate these concepts and stick with it. Know that these topics don't always come immediately. So lots of examples will help us too. And knowing that you have to think. This is not something that you can just lightly go through. So, hope you're ready. I have an example now that develops, that explains really what's going on when we do inference, the theory behind it. So, to illustrate this example, I have a sample of American adults. Sorry, not a sample. I have, well, I'll just say this. P hat is always the sample, the number of successes in a sample over the sample size. And we want to use p hat to study what's going on in the population. So to illustrate this, let's first say we know what's going on in the population. Usually that's never the case. Here, we got a population that's, say, 30,000 people, kind of representative of the United States, and in which we know 88% support solar and 12% don't, right? And so we can make our make our population look just like that. So here's some code where I make my population 88% of them times n. So that would give me the number that support, 12% don't. And so this is essentially 300,000 people. And I'm going to randomly sample from that population. So now we got my sample. And this time I'm going to sample 10. So based off my sample, right here, if I run this and then run this, you can see my sample. It looks like 1, 2, 3, 4, 5, 6, 7, 8, 9 support energy, 1 doesn't. So let's find the proportion that support the expansion of solar energy. That's what we call p hat, not fat, but p hat. And 9 out of 10 is a 90% proportion from my sample. So it's kind of representative. Notice p hat, oops, I don't want that. Just illustrating, we sampled p hat was 9 out of 10, so 0.90. Notice that's close to the actual proportion of the population, but there's a margin of error. So the margin of error will be 9 out of 10 minus what the actual proportion of the population was. We said 88%, 0.88. So there's a 2% discrepancy between what we sampled and what's going on in the population. So next, let's do this, but let's change our sample to 100 and see what happens. So this bit of code that we used earlier for sampling, we're going to want to copy it. So let's copy our sample and see what it looks like when we do 100 people. So everything's the same. We're sampling from that same 300,000 people, and we're going to use replace is false, meaning we're going to sample unique people. And we do 100. Well, that's a lot of people to count. I don't really want to count it. So let's do this. Sample double equals support. This will tell me all the people that support. True. People that support, false that don't. And remember, with a this is called a binomial variable. No, that's not right. A Boolean variable. That's the word. Boolean means true, false, and trues are always counted as one. So if I add up this thing, I'm adding up all the trues. It gives me a count of the trues. Oh, 87 people say true. So the proportion would be out of 100. I got an 80% sample proportion. So in this sample of 100 people, p hat, the proportion of people who supported this expansion of solar energy was 87%. Notice I'm getting a little closer. So let's find my margin of error, 0.87 compared to the 88%. So we're only at a 1% margin of error between these two, between my proportion and my sample. Oops. And the last one, let's do this again. I guess I'll copy all this code because we're going to now do it for a sample of 1,000 people. What do you think is going to happen with 1,000? If I change the sample size to 1,000, and I run this, this will count up the number of people to support, and I wanted to divide it by 1,000 to find the proportion. So I got 878 as my sample proportion. So now I did 1,000 people, I did 878. How does that compare to my 88%? 78. Notice that margin of error is getting smaller and smaller. So this illustrates what we would expect from the law of large numbers, which says that as I sample more and more people, larger and larger samples, it's going to be closer and closer to the theoretical average. So that's the first principle that's pretty important when we're talking about inference. So the next step is if we were to do this many, many times, looks like I have examples of 1,000. 1,000 was a pretty close estimate, right? Well, we can get even closer if we take, I'm going to do this in a different color now. What if we sampled again, and again, and again, and I took all these samples and made a plot of what those are distributed like. I made a histogram. That's what we'll call our sampling distribution. So here's what this code does. It takes many, many samples. We do 1,000 samples, each of 1,000. So if I run that, this plot is what you call a sampling distribution. This says if I were to sample many, many times from my population and took the proportion each time, it would follow some kind of distribution. It's called a sampling distribution. And so as expected, the middle would be 0.88% because that's the population we're sampling from. But even more importantly, the spread of data will help us determine some kind of certainty with which we can know what we're measuring. How do we know any difference that we observe is not due to chance? This is where we begin to answer that question. So we sampled 1,000 times and we got 1,000 proportions from this iteration. Again, we wouldn't be able to do this without a computer. But now that we have that, we can take the mean of those samples and the standard deviation of all those samples. So we've sampled 1,000 times. We've gotten our p hat. We got the mean and the standard deviation of this. And if you want to, you can do this for 10,000 samples. Run p hat for 10,000 times. It's going kind of slow. This will be a good illustration. Notice the graph gets smoother. And if I want to find out the mean and the standard deviation of these 1,000 samples, notice the mean is really, really close to 0.88, but the standard deviation remains the same. So, there's still going to be variation on my sample. So that variation is what we're going to study next. Okay, so here is a theorem that talks about how distributed my data is going to be from my mean. It's called the central limit theorem. It says if you sample again and again many times, that sample that you take from your population will have a mean that matches your population mean and a standard error that looks like something like this. This is the standard deviation of what you're sampling from. Okay, so this is really the central tool we're going to use for doing our inference, and it changes just depending on what kind of data we're using. So let's look at the conditions for this central limit theorem to hold. It says n times p needs to be greater than 10. If n is the sample size and p is the proportion of the success, n times p is the number of successes. They have to be greater than or equal to 10. N times 1 minus p, well, 1 minus p is the chance of failure, so number of failures has to be greater than or equal to 10. So those are the two conditions we're going to check. This just ensures we have a big enough sample size. So when we did this, p was 0.88, n was 100, 1,000, n times p, and n times 1 minus p. This is the number of successes and the number of failures in my sample. Turns out, yeah, they're big enough. We got a really big sample. So that's just something we check when we're doing our inference. So now we can compute theoretically what the mean of this distribution will be. The central limit theorem says, hey, it's going to be 0.88. P is going to be 0.88. I want to see what that is. And the standard error, this is that formula we saw up here. This will describe how spread apart my data is. It's going to be p times 1 minus p divided by n. That's going to be what my standard error is. And notice that's basically what we got up here. We took the standard deviation of that big sample. So this just confirms what we found up here. All right. So now this tells us if we sample from that population, sample of size n, many times, what we'll get is something that's normally distributed. That's what the theorem says. P hat is normally distributed, and we can write this as mean 0.88, standard deviation. Oh, well. So we can do things like, hey, based on this theory, we can say how much of the time will I expect to sample something that's within 1%, that has a sample proportion that's in 1% of this. So I would say P norm. Well, let's draw the picture first. This says if I have something that's distributed 0.88 with standard deviation 0.0102, what's the proportion of times that would be within 1%? 1% to the right, 1% to the left. What's that area? So, like I've been teaching you, this skill of finding our probabilities now comes into play in a big way. So the mean of this distribution is 0.88, standard deviation. I'm just going to copy this. So that would find everything that's below 0.89, but we're going to have to subtract everything that's below 0.87 to get the area in between. So this will tell me about 67% of my data is going to lie within 1% of that actual population value. So 67% of the time that I sample from my big population, it's going to be within this bound. And the last question, this answers asks how many times would I be within 2% of my sample population? In this case, we're looking at everything 2% to the right, so that's 90, 2% to the left, that's 86. So what would that probability be? So I'll go from 90, 86. This shows me about 94% of the time I'd be within that range. This helps us start to get confidence on something that we're measuring, confidence that the population lies within some bound that we're going to determine based off our data. So that's the first part. Come back for part two to learn how to apply this for making confidence intervals. This is a really practical thing we can do with any proportion. We can find a confidence interval. The calculations are relatively simple, but they do rely all on the theory which I've just described. Okay, so we'll see you in class for questions, and good luck.